and the violet one right next to it. Same angle of incidence. Which one is going to bend more?
The red, since it's faster.
So I heard violet and I heard red. So why the red, why the violet?
The index of refraction is larger, so the angle will be.
So the angle will be smaller? That's right. Okay, so for air, this is, let's say 1. It's 1.0003 or something, right? Let's just say 1. And for this one is whatever, right? It's something higher than 1 for the glass. So if we write n sine theta in air for medium number 1 equals n sine theta inside the glass, right? So this is the same for both colors, right? So in air is not dispersive, so the index of refraction is the same for both red and violet. They came in with the same angle of incidence, so this is the same, so this is a constant. So the color for which the index of refraction is greater, like violet, right, is going to have to be the one with the smaller angle measured from the normal. So the violet one will then go like this, and the red one will bend, well, less. Although that doesn't look like it bent. Sorry, I'm not a good artist today. Not that I've ever been, but let's exaggerate. Violet is going to go this way, and the red one is going to go this way, instead of going straight. Yes?
Is this why we?
It's like prisms.
I was gonna say the same thing. Is this why we have the prism? That kind of picture.
So yes, so what I'm getting at is that by the light entering from this medium, where all the colors travel at the same speed, because the index of refraction is the same for all of them, because the air is non-dispersive, when it enters into this medium, which is dispersive, so that the index of refraction is different for the different colors, then the light rays are going to have different angles of refractions. And because they have different angles of diffractions, that means that they separate or they disperse. And if I put, I cut the glass so that now this is the glass here, right, still, and this is air. By the time these light beams reach the other end of the glass, they will be spatially separated, they'll be separated in space. And so now when they travel in the, and I can just go like this so that you can call this a prism. If you draw the normal over here, will the red light travel away from the normal or towards the normal when it goes from the glass back into the air? Away, correct. And what about over here? For the violet light, will the light ray bend towards or away from the normal when it travels from the glass, where it travels slow, back into the air where it travels faster? Away. So if you put a screen over here, and you send in the two colors together, by the time they hit the screen, you're going to see a red spot over here, and in a separate location, you'll see the violet spot. And you can imagine, green is between the violet and the red. So if I included a green beam of light in this here, the green is going to go between them. And it's going to hit, then that'll be green. And what if I send in white light, which is the combination of all the colors put together? Then the different colors in the spectrum, right? All of these different colors, will have slightly different indices of refractions, so they will refract by different amounts. They will disperse inside the glass prism, and by the time they come out on the other end, they will have come out, well, dispersed. So That's the idea of the glass prism that you see in that picture. Let me give you another argument. Let's go back to the question. Remember when I said if you have the red and the violet light coming in, I said which of the two colors, the red or the violet light, will refract more, right? Will bend more towards the normal. I think I didn't phrase the question as refract more. I said which one is going to bend more towards the normal, right? That was the question. And then, we were told that, well, the violet one, because for the violet, the index of refraction is greater, so the angle of refraction has to be smaller, right? So we use that argument. Another way to think about that, to answer that question is the following. Suppose that in some weird units, right, the speed of light in this medium, let's say V1, or let's just say V, is 10. Not meters per second, because light in air travels a lot, like pretty much just a little bit more slowly than in vacuum, around 3 times 10 to the 8 meters per second. But let's just say that I convert that to some newly invented units, and the number comes out to 10. Give me a good number for the speed of light of the red light in the glass prism. What would you say? Just, is it faster or is it slower? Slow. So it would be a number less than 10. How about we pick 8? What would be the speed of the light that's violet? What would be the speed of the violet light in the glass?
Like 7.
7, something even smaller, right? So notice that one way to think about it conceptually is like this. The wave that will experience the greater change in speed, the more slowing down or the more speeding up, is the one that will refract more. So if you compare the red light here in the glass is traveling at 8, well, while in air it was traveling at 10. So, it's like it went from 10 to 8. So it refracted so much. But the violet one is traveling at 7 compared to when it was initially traveling at 10. So it actually slowed down more than the red. So it refracts more. Yes? That's another way of thinking about it. But then one has to be careful, because what if I ask you this question in this same problem, right? What if I ask you which of these two light rays will have the smaller angle of refraction?
Violet.
The violet one, right? So notice that having a smaller angle of refraction is equivalent in this problem to saying it's the one that refracts more. Because when I ask the question, which one will refract more, you might be thinking, oh, the one with the higher angle of refraction is going to be the one that refracts more. But that's not the case, right? I think of refraction as, if it refracted a lot, it means that it was traveling in some direction, and then it bent and it went in a new direction, and the more it bent from the original direction, the more it refracted. But because in this case, it bent more towards the normal, the angle of refraction is actually smaller. So in this case, the light ray that refracted the more is the one that has the smaller angle of refraction. So there are two different questions. Yes? Okay. Hence, that's how prisms work. And one person, I think the person who was one of the first, if not the first, to claim that white light consisted of all of these colors in the visible spectrum put together was Isaac Newton. Newton is famous for his theory of motion, right? Invention of calculus. But Newton did also experiments, conducted experiments with light, and actually he claimed that light consisted of particles, and he also realized that that all the colors in the spectrum put together gives you the white light. And the way that he was able to, convince himself of that, or figure that out, is because he knew someone who was able to cut a couple of prisms for him. So I guess some people had just one prism, or maybe they had more than one prism, but people usually sent in white light, let's say sunlight, and then the light went through the prism, and then you had this, then you observe this spectrum, on the other side. And so people thought that maybe something was going on in the prism that was making that light, the different colors of the light. But then Newton was able to put another prism over here, another glass prism, and then he was able to put them back together, and then he made white light again. So then he reasoned, it's not that the thing is making the colors, or then you put them together and then it makes the white light. It's just that the white light itself is composed of all of these colors put together. And what the glass is doing is just separating them, and by putting another prism appropriately positioned, it would just recombine them back into what white light is, which is a combination of all of these colors put together. This phenomenon of dispersion can be used to explain how rainbows are formed. So how are rainbows formed? So we have this picture here. So what happens if you consider a water droplet, imagine a water droplet, spherical water droplet. So this is water, and then this is air. Right? Just a chunk of water, right? And what if you send in a violet beam of light and a red beam of light coming in from the sun? So that would be, so these circles over here represent water droplets. That's one water droplet. That's another water droplet. And you have sunlight coming in from here. So what's going on in this picture is the following. So when you observe a rainbow, you have to be looking towards the storm, towards the rain, towards the, in the direction of the water, with the sun behind you. Not with the sun over there, not with the sun over there, but the sun behind you. So light comes in from the sun, right? So here you are, you're looking that way, and the sun is here, so sunlight comes in like this, right? And it's got all the colors put together, right? So then when it enters the water droplet, let's say like this, right? I'm just gonna consider the red and the violet together, right? Coming in, and the blue and the green and the yellow, all of them, right? Now, when the light refracts into this water droplet, will they bend towards the normal or away from the normal? Towards the normal. And which one is going to bend more towards the normal, the red or the violet? The violet. So then I have to draw something like this. I have to go like this for the red one, and then just something more, more refractive for the violet one. And then some of the light is going to go through, right? It's going to refract back from the water back into the air, and that, that allows you to see the mountain that's behind the rain or whatever, right? But let's consider the reflection now at the back surface of the water droplet. So if you consider the reflection, right? So if you draw the normal to the surface over there, and then normal to the surface over there, what happens is the red light will, the angle of incidence has to be equal to the angle of reflection, so it's going to go like this. And the angle of incidence over here has to be equal to the angle of reflection, so it'll be something like this. And I'm not doing as good a job as they did over there. But then the point is that over here, you got the, I guess I should have thrown this one more like that. But you get the picture. And you have a normal over here. So by the time they come out, both of these, the red and the violet or purple, will bend away from the normal, right? And so the red light is going to jump, the violet is going to go like, instead of going straight, it's gonna go away. And then the other one is going to go, away like this. Anyway, what I'm saying is that if you consider a water droplet, one of zillions of water droplets in the rain, and you have sunlight coming in, right? Light travels from the air into the water, and the white light coming from the sun disperses inside the water droplet, and then they hit different spots at the back surface of the water. Part of the energy goes through, but the rest of the energy is reflected. And when, and the angle of incidence is equal to the angle of reflection, right? Typical reflection law. And then they hit over here, and then they come out, and they come out separated. And this person, for example, this person, right? If this person looks straight up, let's say I'm here and I'm watching a rainbow. So if I look in that particular direction, for example, suppose I look in that particular direction, so many degrees from the horizontal. If I look in that direction, let's say I'm looking in the direction of the red light, that's coming towards me from a water droplet, right? That refracted, reflected, and refracted light from the sun. And then that one is lined up with my eyes. Now, if this red light is coming to me straight like that, right? If I have red light coming in like this, what do I think, right? Light travels in a straight line, so I think that the source of the red light is over there, just shining red light towards me. So if you keep looking straight, you think that the red light is coming from here, and that's when you see the top of the rainbow. And what ultimately what matters without getting into the details is the angle that you look at from the horizontal, from your eye level. So if that happens to be 42 degrees or whatever the angle is, I don't know what the angle is, but somewhere around there, then I'll see red light. So if I think of the horizontal, like, I remember we have a ruler here. So if I think of the horizontal like this, and suppose 42 degrees, if I look that way, that's red, but it's the same if I look at 42 degrees this way from this one, and that should be red. So therefore, that's why I see half a circle. Now, what do I need to do in order to see the violet light, like the other end of the rainbow? Well, if I want to see violet light from these droplets, the ones that allow me to see the red one, I have to jump, and then line up, and then see, and then I'm going to look this way, and I'm going to be looking in the direction of the violet, or I think it's going to be, violet light is produced over here, or I'm looking at the source of violet light. So it's easier to just, because what matters is the angle at which the light is coming in relative to this. Since you have water droplets, falling all over the place in front of you, just look at this process happening with a water droplet further below the sky, right? And so then if this is the same as this, it's just that this is lower and that's higher. And in this case, notice the violet comes at the top, the red at the bottom. For this one, the violet comes at the top, the red at the bottom. If you look in this direction, you're going to be lined up with the violet one. And then, of course, what you think is that the light is coming, well, that's the rainbow right there, for the end of the rainbow. So that's the violet, and that's the red, and then all the other water droplets over here, right? If you look in the directions in here between this and that, you'll be looking at the other colors in the spectrum. So the red will be on top, and the violet at the bottom. Make sense? In fact, it doesn't have to be raining for you to see a rainbow. You could be walking over here on a sunny day, and if the sprinklers are on, right, you're walking on one of these cement paths, right, and then you got grass over there, and maybe the sprinklers are on, and if you look in the direction of the water over there, and the sun is over here, you might see a little rainbow over there. So it doesn't really have to be raining, right? So the point is that this rainbow, this primary rainbow as it's called, it's really formed by the refraction, reflection, and refraction of light from zillions of water droplets. And what happens is that since water is dispersive, it's a dispersive medium, when the light travels from the air into the inside of the water droplets, the different colors of the white light coming from the sun, right, then disperse. And if you look in the correct directions, you'll be able to see red, orange, yellow, green, blue, and so on, and the violet at the bottom. Now, why do you not see a full circle? Right, so let's say I'm like this, right? And so suppose I need to see red and I see something like 42 degrees. Well, if I want to see the bottom half, I'll have to go 42 degrees from here below, right? If I look this way, what am I going to see?
The ground.
The ground. The water stops at the ground. But what if you're in an airplane and you look at the window and it's raining and the sun is on that side and the rain is over there? So because you are at some high altitude above the ground, you could have water droplets above your eye level and water droplets below your eye level. And then you could see a full circle. I've never seen it, but I hope that someday I can see it. Every time I fly, I look at, to see, but that would be cool. Has anyone ever and in fact, you don't have to be in an airplane. I think some people have told me that maybe they went to Yosemite, to some high peak, some high mountain, and then you're over there and there's this big drop and then it's raining and then you can have water droplets above and below and you can see a circle too. Has anyone ever seen a full circle? Some of my former students say that they have seen it, and interestingly enough, a lot of them say, yeah, flying in Hawaii. I've never been to Hawaii. I need to go to Hawaii.
How do you explain the double rainbow?
So that's the next picture.
Oh.
So what happens in the next picture, the double rainbow, the secondary rainbow, is formed by water droplets that are higher in the sky. And what happens in that case, as if this was the primary rainbow with the red on top and the violet on the bottom, right? What happens is the raindrops higher in the sky, right? So you have the light coming in like this, but instead of coming in at the top and then boom, 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 coming out at the bottom, it comes in at the bottom, but then notice how many reflections are there in the back surface of the water droplet before it comes out. And how many were there in the previous one? Let me show it to you again. There was only one reflection in this primary rainbow. But in the secondary rainbow, right, because of the light coming in at some angle, boom, boom, there are two reflections. And what happens is that the second reflection flips the colors again. So what you see then in the secondary rainbow is that the order of the colors is reversed because of that second reflection. Can you see that in the secondary one, the red is on the inside with the blue, violet on the outside, while the primary one, the red is on the outside and the blue's on the inside. So that second reflection at the back surface of those water droplets that are higher in the sky allow you to see another rainbow with the colors flipped. So the next time you see those I've seen.
Yeah.
Those I've seen a few times. And it's I've taken pictures of it. Maybe I should use my picture instead of that one. But it was just beautiful. I think one time it was like right here at OCC. I mean, a couple of years ago. Well, it was before the beginning of the pandemic. Yeah, where was it raining? I think the sun was there and it was raining on this side, and it was just stepped out the Lewis building and it just had this beautiful display of light. I can only imagine people that didn't take physics, and this had not been discovered. Just think about people 1,000 years ago, 2,000 years ago, 3,000 years ago. They saw that. It's like, my goodness, something is going to happen, right? I mean, you would think the gods are upset or whatever, or maybe they're happy or whatever, right? Oh, there's going to be a pandemic coming along or something, right? But it's just, but it's been figured out that what's happening is just the reflection and refraction of light from zillions of water droplets, and water is a dispersive medium. And you can see a rainbow. You don't really need a glass prism cut like this to see a rainbow. Sometimes, depending on the angle at which the sunlight enters a window pane, right? You may see a little rainbow on the carpet or on some furniture inside your house, right? You see a little dispersion of light, of white light, of sunlight. I mean,
the light from the sun is coming through vacuum and then it comes into air, does that mean it's also reflecting when it comes into our atmosphere?
And refracting, and I have it over here. So, I'll make a couple of comments to that end. Say you go to Laguna Beach, and you are there with your significant other, and the sun is about to set. Wow, what a romantic moment. And you see the sun over the horizon, and that's the horizon. And you know, see the ocean, and you're watching, and then here's the sun. It's about to start setting. Oh my goodness, let's not miss this, you know. And then you start watching the sunset, and you just watch, right? And so the truth is that the sun is already over the horizon when you're looking at it. It's already over the horizon. I mean, you know, if I'm in Laguna Beach and I'm looking west and I see the sun, it's about to set. I mean, where do I think the sun is? I mean, if I see the marker over there, the orange one, and I wanted to grab it, there's no reason for me to grab over here, right? Remember we talked about this last time? I would just go straight because, you know, the light travels straight from the markers to my eyes. That's what we are trained to do, right? I see my, you know, keys there, my note. There's no reason. I want to grab my notebook. I don't go like this. I don't go like that, right? I mean, I see it right there. The light goes straight from the notebook to my eyes. We talked about Fermat's principle of least time, where the light takes the path of minimum time to make the trip. So if you got so inspired by the beautiful moment and the sun is, you know, about to begin to set, and you say, oh, honey, baby, I love you so much. I mean, I'll just give you the world if I could. In fact, if I could grab the sun, I'll give it to you. Now, where would you reach if you wanted to grab the sun? I mean, you see the thing right there in front of you, right? Where would you reach? Well, okay, let's imagine that for a moment I can stretch my arm and grab the sun and bring it and just give it to you because you deserve it, because you're the best in the world, right? Where would you reach? I mean, if that thing right there is the sun, if I see the sun right there, that ball over there, right? I mean, there's no reason for me to reach over here or over there. I'm just gonna go like this. Imagine my arm extends, I grab the sun and then I give it. Well, where would you reach? So in this picture over here, if you're standing over here, right? And you're watching the sunset, right? So the light comes from the sun from over here. Here's the normal to the, let me maybe say more about, maybe the picture is good enough, but the light is traveling from the sun to the earth, first in vacuum and then in the atmosphere, where it's going to travel more slowly than in vacuum. So here's the earth, right? And I'm exaggerating the size of the atmosphere. So this is the atmosphere, right? And so let's say here you are, right? With your loved one, right? And you're looking in the direction of the horizon, right? And so what happens is, well, the sun is really over here. And so the light comes from the sun like this, right? Here's the normal. Is it going to bend towards or away from the normal as the light travels from where it travels the fastest in vacuum to air, where it's slower? It's going to bend towards the normal, right? So the sunlight is going to then bend like this, right? Well, that's supposed to be straight, and then it goes to your eyes. Now, where would you reach? You think the light arrives like that to you, right? So you think the light is coming in straight. You think the sun is over here. So it's in fact over the horizon already. You're looking at something that's already below the sun at that instant. One more comment. How long does it take the sun to actually set Suppose that's when the sun is about to set, and this is the horizon, and then it's gonna be like that, right? And then it's gonna set. How long does it take you to do that? Have you ever timed it?
An hour? I don't know.
Huh?
An hour?
5 minutes.
Depends on how long we're watching.
No, it takes about 3 minutes.
We're talking about from it's like on the horizon.
From
all the way down.
here,
Oh,
from when
okay.
it's up beginning, to when it just, dude, you don't see it anymore. Next time, time it. Just take out your timer in your cell phone. Honey, baby, let's time this thing. Let's do an experiment. Let's do an experiment, right? And then time it. And it'll be about 3 minutes. So that means that even if the light, if you didn't realize that there is atmospheric refraction of light, even if the light went from here, straight, right? Actually, how long does it take sunlight to reach the earth?
Like 8 minutes, 30
8
seconds.
minutes and 20 seconds on average. Well, let's say 8 minutes. Well, if I see the sun, if I'm here and I'm looking at the sun, right? Those are photons of light that are entering my eyes right now when I see it, but those photons of light left the sun more than 8 minutes ago. And during those 8 minutes, since it only takes like 3 minutes to set, it went down. So for sure, it's over the horizon. For sure, it's over the horizon when you're looking at the sun. So yes, the light refracts as it goes from the sun to us when we look at it, on a sunset. Right? If you're over here and it's noon time and the sun is over there, right? So the light goes through. So it goes through, so not a problem. But there is atmospheric refraction of light